material on this, and part of it was discussed. I'm going to go just a little bit of background about the patents and why we're at where we are. That was discussed by someone else from Ridgewood, so I'm just going over this. So my part was about research. When we took the consensus, there was no question. We just said we want research on everything. We want the government to do it and to fund it. So that was what happened with the consensus. But I thought that maybe to give a little bit of background about the new technologies and what kind of research is going in, particularly how it applies to agriculture and also to our consumer stuff. It was mentioned, Ellen mentioned a little bit, and Fran went into it also. So, what's the purpose of research? I'm going to read little sections. I hope I don't have to read the whole thing. The ultimate purpose of research is to assess risks, protect and improve long-term agricultural productivity. This is when we're talking about agricultural research, water quality, and habitats for organisms, while balancing transparency and encouraging innovation. So this is always what the balance is. Well, if it's transparent, and will people continue to do research? Okay, and a little background on the status of research. What's happened because of the change in patent laws? Much research is carried on at universities and small and nonprofit organizations and small research companies, new startup companies. The government used to fund much of the research and own the inventions at that point. The government, if they funded it, they owned the inventions. In 1980, a law was passed. It's called the Bayh-Dole Act, and these which allow the organizations now to maintain ownership of their patents and ownership of their properties. And the intention behind this private ownership was to speed up development, to make development more applicable for practical research, from taking it from basic to practical, and also to encourage more innovation. The government lost control of the new inventions. I mean, that was the outcome of it. We traded one thing for something else. Developments in the laws since the 80s have given incentives for large multinational organizations to invest in seed R&D and all kinds of agricultural research. And as of 2012, 5 major companies, mostly American, but they're also becoming more global, provide 80% of the U.S. corn, 70% of soy seed, and the companies, I'll just mention them, it's some of them are familiar: Monsanto, DuPont, Pioneer, Dow, Agriculture Sciences, and Syngenta. And as private investment in R&D increased, public investment has stagnated through the 90s and has fallen dramatically. So very little public goes into it. So these small companies come up with the research, and these large agricultural companies buy it. They hold the patents, and the research. I'll talk a little bit more about how this happened. Yeah, there was a question. Was there? No. Okay. All right. So how did this go on? Until the beginning of the 20th century, farmers saved their own seed and shared seeds. By around 1915, a seed certification program started, and this was encouraged by the big land-grant colleges to help improve the quality of the seed, and it gave rise to the birth of private seed companies eager for distribution. Research and development was done by these public institutions. It was funded mostly publicly, and the farmers enjoyed the results. By the 1930s, the development of high-yield corn, the rapid expansion of U.S. seed industry and balance began to shift from the public research to private enterprise because there were profits to be made. So this is really the beginning of how these large multinational organizations got involved in our food supply. Let's put it that way. Okay, that's really the beginning of it. All right, what are the problems with the consolidation of research in these large global corporations? Well, we know some of them, but independent research and testing to assess the risk is limited because the patent laws, which allow the institutions to own the projects, also prohibit outside organizations from doing their own research. They just aren't allowed, and that includes the FDA. have to understand that when the FDA approves something, that the FDA is using research that these companies have provided for them. Supposedly, the outside research is independent, but how independent is it? We see studies now, I've been reading some studies that supposedly are sponsored by universities, but their labs, they don't even know it sometimes. The labs are being funded by some of these organizations, all right? So the laws were set up so that until the FDA will approve something, and then the information maybe will be released so that more independent research can be done. All right, the second thing, if firms with patents on seeds or genetic traits, which I'll talk about a little bit later, are allowed to place restrictions on the use of their products, and these restrictions often exclude independent research on productivity claims. But more important on these restrictions is research for health and environmental impacts. So the firms submit the data on their research, and that's what's out there. And the third thing is that there's a loss of biodiversity. That these companies have one kind of seed, and that's what's out there. One kind of corn, one kind of wheat, and that's it. They're just, that's the big problem, and that's what's going on right now. Okay, the fact is that this is kind of the background on the status of where the research is on the new technologies. And I'm going to explain a little bit about some of the new technologies. Some of you may be very familiar with what GMO, or what genetic engineering is, and some of you may not. And I also, if there's time, I'll talk about one of the other new technologies, nanotechnology. And Ellen alluded to it in, it didn't call it that, but it's used in field monitoring. Some of you were talking about using computers. Nanotechnology comes in there. Okay, back to history. We all know about Mendel. Greg Mendel was the first one to really figure out that there was something in there about genetics. He's the father of genetics. And he realized that if you took a red, we all remember from sophomore biology, took red peas, flowers, and white peas, and you put them together and you got pink ones. All right, so since then, for hundreds of years now, we've been crossbreeding, selective breeding for certain traits. This is done. As they got more advanced, we had hybridized fruits and vegetables, and jello, the clone plots. But this was done by selective breeding, constantly breeding things, selecting for the things that we wanted, hybridization, grafting, this kind of thing. Okay? So this has been going on for hundreds of years. All our products are not natural. I mean, it's natural in the sense that they have been derived from farming techniques. What's new now is that, one other thing that I should mention, in the 1920s, it was discovered, another technique was used, we started to get a little more technical, by taking seeds and irradiating them, causing mutations, planting them, and then selecting for the traits. Okay, but again, this is selection, taking seeds, doing something to them, perhaps not so natural, but then selecting. So that was done. What is genetic engineering? Well, this is the definition of it, how it differs from what I've just mentioned now. By definition, genetic engineering is the genetic manipulation of an organism's genes by introducing or eliminating or rearranging genes using methods of molecular biology, also now referred to as synthetic biology, and called recombinant DNA. What this means is that a gene from another species can be another plant, can be from an animal, is inserted into the gene of this plant. Completely foreign gene, and it's done by using viruses and various techniques. You have to get it in there. You have to get this gene to, this organism to accept the gene. That's what it means. So we're working now at the genetic level and messing with, I'm using that really, I guess that's pejorative because I don't want to form an opinion exactly, but this is what genetic engineering is. You've got forming something completely new at the genetic level. Why is it done? All right. It was done for higher yield, for decreasing disease in plants, for making plants insect resistant, to make them herbicide resistant. I'll talk about that in a minute because you may be familiar with that. To enhance nutritional value, that's a positive. To allow plants to thrive under unfavorable conditions, drought, or too much water. You can get a plant perhaps to thrive where it wouldn't have been able to thrive before. For increased pharmaceutical value, and to create plants that are even effective for removing pollutants from soil or water. So you take an organism that's, and you put in a gene that it didn't have, and it's given it a new trait. Okay, there are two kinds of genetic engineering. One of them is called, and these terms aren't really necessary, but trans, because you hear about transgenes, transgenetic engineering. That's where they take a gene from a different species completely and insert it. And then there's cisgenesis, where it's a similar plant, like two different, and they do this with potatoes. This potato is resistant to one thing, this potato is good for something else, and they'll take the gene from one and put it in the other one. That's called cisgenesis, where you've got the same species, and it's similar to breeding, even like dog breeding. Let's just go with something we're familiar with. Then it's faster. You know, you don't have to wait for generations. You take the gene, you put it in. Okay, so that's done. There are two terms that are constant. You may see this: BT, which is insect-resistant gene, and HT, which is a herbicide-resistant gene. Okay, a little background. When was it first used on a commercial scale? Actually, the first use of it was to create synthetic, or let's say biologically engineered insulin. Originally, insulin for diabetes was obtained mostly from pigs, but pigs and cows, and it was purified and then used in humans. Well, there's always a problem with insulin is a small protein. It's actually a peptide, a very small. It's a protein, and proteins cause allergies. And people sometimes had trouble, their bodies rejected the insulin. So they were able to take a gene to produce insulin from humans, put it into bacteria, and now the bacteria produce the insulin. And it's grown in a laboratory. It's pure, and it's human insulin.